Then next, a source X with zero internal resistance is shown in figure 1. The voltage of X is linearly dependent on temperature and produces a current I from 0 to 20 milliamperes for the temperature ranging from 0 to 100. The current is linearly converted into a voltage between 0 and 5. Linearly converted into a voltage between 0 and 5. 5 volt range, and is measured across the resistor R as output voltage V. Okay, diagram is given, circuit diagram is given. Then A1. If R is an ohmic resistance, sketch the IV characteristics of R. Right, if ohmic, it follows V equals IR. Right, if ohmic, we know it follows Ohm's law. V equals IR. Then when we plot V and I, right, this is like V equals RI, no? If you plot V and I, right, I is the x-axis, this is the gradient, this is the y-axis. That's a y equals mx. That's a y equals mx. Right. That's a y equals mx. Then, right, should be a straight line, goes through center. Should be a straight line, goes through center. Right, y equals mx. Right. Then second one. Second one. What should be the value of resistance of the resistance R? What should be the value of the resistance R? Okay, then maximum current it is going to flow is 20 milliamperes, no? And the maximum voltage is 5 volts. Then for R, delta V equals IR. Delta V is 5. Maximum current that is going to flow is 20 milliamperes. 20 10 to the minus 3 R. Then R equals, right, this is 5000 over 20. Then R equals 250, no? 250 ohms. R equals 250 ohms. Right? 250 ohms. Next, part 3. Calculate the values of voltage and current across the resistor when the temperature of X is 25 degrees Celsius. Hence, find the power dissipation in the resistor. Okay. Calculate the values of voltage and current. Okay, it says the voltage changes linearly, no? Voltage changes linearly, which means voltage and temperature are linearly changing from 0 to 100, right? It is like this. Then when temperature varies from 0 to 100, voltage varies from 0 to 5. Then if temperature is 1/4, voltage should be 1/4. Then new voltage is 5 over 4, 1.25 volts. New voltage is 1.25 volts. It follows the same ratio. It should follow the same ratio. Right. Then voltage and the current. Right. Then the new current is right. New current is new current. Now voltage is at 1.25 across this one, no? 1.25 across here R. Then to find new current again for R, delta V equals IR. Now delta V is 1.25, right? And I need new current, say I dash, and R is unchanged, 250. R is unchanged, 250. Then I dash equals, right, 1.25 over 250. 1.25 over 250. Then if this source 125, this is 2, no? Then this is 0.02. 1 over 0.02. 1 over 0.02 means 5 times 10 to the power 3. 5 times 10 to the power minus 3. Right? Then current is 5 milliamperes. current is 5 milliamperes. 5 milliamperes, right? And hence find the power dissipation in the resistor. Okay, right? Not over yet, right? Now the power dissipation. Then power dissipation of the resistor is given by, if the current is known, I squared R. Power dissipation is given by I squared R. If current is known, then I squared is 5 times 10 to the power minus 3 squared. R is 250. R is 250. Then 5 squared is 25. This is 10 to the power minus 6, right? 10 to the power minus 6 times 250. 25 times 25 is 625, no? Then this is 625, then 0, 10 to the power minus 6. Then we can keep it as 6.25, 10 to the power minus 3 watts. So that is 6.25 milliwatts. 6.25 milliwatts. 6.25 milliwatts. That part is done. 6.25 milliwatts. Right? Part B. Part B. Suppose that resistance R1 is connected parallel to X and the wire segment BC. R1 okay, is shown wire segment BC, and the wire segment BC in the circuit shown in figure 1 is replaced by a resistor R2 as shown in the figure 2. Okay, let R remains constant at the value calculated in A2 above. That was 250. Right, first one. When the source produces a voltage Vs, right, Vs here, Vs, write down an expression for the current I passing through resistor R. Okay. When the source produces Vs, okay. Then, right, if the source produces Vs, right, right, we know this Vs is between A and B, no, which means VAB equals Vs. Because that is between A and B. And total resistance, now this same I flows to this, no? Can you see that these two resistors are in a series combination? Right? Which two? R2 and R. R2 and R in a series combination. And they are seriously connected between A and B. Right? They are series between A and B. Then what we need is current, no? Then apply delta V equals IR. Delta V equals IR for the branch AB or BA. AB. For the branch AB. AB or BA or BA. Right? For the branch AB. Right? Then R AB. Delta VAB is Vs. Right? I need I. And total potential from A to B is right, that is actually BA. Current flows in the opposite direction, no? Then these two should be BA. Current flows in opposite direction. Right, then BA, right, and B A. See? Right, then RBA is R2 plus R, no? R2 plus R. Then Vs equals I times R2 plus R is 250. Now we need I. I equals Vs over R2 plus 250. Right? See, I is this. Now I is known. Right? Then part 2. Right? Part 2. Hence, write down an expression for the source current IS. Okay. Then IS is the addition of IS is a sum of these two currents. Now let's assume the current flows here as simple line, right? Now first I can find simple line. First we can find simple line. For R1, see, for R1, apply delta V equals IR. For R1, delta V equals IR. Then delta V is Vs, no? Equals current is simple line R1. See, now simple line is known. That is VSO R1. That is VSO R1. Now, I know IS has divided into 2. Since IS has divided into 2, right? See, now be with the question from the beginning. Always when you do essays, it has a nice flow, right? Always it has a nice flow, right? We have to always be in the question, be with the focus in the question from the beginning, right? When you are going in that flow. Then IS is the addition of I plus simple I. Then capital I was Vs over R2 plus this thing, no? Right? So that is Vs over R2 plus 250 plus simple I was Vs over R1. Then this is IS. This is IS. Right? This is IS. Hence, write down an expression for the IS. Okay, expression is here. Then IS is given by this. Expression is here. Part 3. Part 3. Right? These are the 3 most recent electricity questions that has been there. Right? Most recent electricity questions. Right? Part 3. Using the expression B1 and B2 above, state what will happen to the ratio IS to I if R1 is very greater than, extremely greater than R plus R2. What is the physical significance of this? Physical significance. Okay. Then we have 2 equations for I and IS. No? Yeah, we have 2 equations for I and IS. Then let's divide these two. We need ISOI. Then IS is, see, IS equation. For IS equation, if you apply a common denominator, it is R1 times R1 plus 250, right? And the top becomes Vs R1, right? No, Vs is common, no? Let's take it out. Vs is common. If Vs is out, then R1 plus R2 plus 250 comes here, right? So this is equation 1, right? And for I we have Vs over R2 plus 250. I is Vs over R2 plus so R1 plus R2 ne. Then R1 no R2. This is R2, right? I'm gonna make R2. This is R2, right? Then R2 plus 250. Say this is equation 2, right? Now divide these two. We need ISOI. Divide these two. See what happens. Then IS over I. That is 1 over 2 from my equations. 1 over 2, right? 1 over 2. Then ISOI equals from IS Vs times R1 plus R2 plus 250. R1 plus R2 plus 250 over R1 times R2 plus 250. R1 times R2 plus 250 over I. Then it becomes a reciprocal. Then here it becomes R2 plus 250 over Vs, right? 250, yeah? 250 over Vs, right? Now, see what happens. Vs cancels. R2 plus 252, R2 plus 250 cancels. Then ISO I becomes, right? ISO I becomes R1 plus R2 plus 250 over R1. Right. Now, what is the given condition? R1 is greater than R plus R2. Then let's convert this to R. That is easy to compare. No? 250 is R. No? 250 was given as R. Then R1 plus This is R2 plus R. R2 plus R. R2 plus R. R2 plus R over R1. Right. See what happens now when this is extremely greater. Right. When this is extremely greater, when R1 is extremely greater than this one, right? This addition goes to, right? If this is negligible, if this part is negligible with respect to R1, R1 goes to R1, this addition goes to R1, right? If that is extremely greater, then denominator that is also R1, then it becomes 1. Then what is our final output? Final result is then IS over I becomes 1. IS over I becomes 1 in that case. IS over I becomes 1, right? Then the question is, what happened to the ratio? It reaches 1, right? It's equals to 1, right? It equals to 1. And what is the physical significance of this? IS to I equals 1 means, now what's happening from this is, IS equals I, no? When IS equals I. Now if IS equals I, this simple I becomes 0. Simple I becomes 0. Then what happens is, hence, 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 simple I becomes 0. Then physically what happens is, if simple I becomes 0, right, there's no current flows through, right? There's no current flows through R1, no? There's no current flows through R1. Then physically what happens is, I equals 0, then no current flows, no current flows, no current flows through R1. No current flows through, no current flows through R1. Right, then physically, this is what is happening. No current flows through R1. Right, see, that's a beautiful flow. Right, that was a nice and beautiful flow. Today also, will you be discussing only 3 essays? In this tute, I have put only 3 essays. Right, 25, 24, and 23 essays. Right, 3 past papers. Okay, right, that was a good part. Huh? That was a good part. Then, moving on, part C. Part C. See to which that is linked to. Right, part C. In a computer hard disk drive, HDD data is stored. HDD data is stored by magnetizing tiny regions of a thin film deposited on a flat circular disk, as shown in the figure 3. A cylindrical rod passing through the axis of the disk is used to spin the disk. When the disk spins, the information stored in the disk is read as an induced EMF. Right, now it is going to link to magnetic induction. Right, magnetic induction again, induced EMF generated in the read-write head, which is a conducting read-write head, which is a conducting horizontal square loop of side length d placed just above the disk. The disk is spinning with a constant angular velocity omega. Right, when located at mean distance r from the center of the disk, passes under the conducting loop where r is very greater than d. The magnetic region produces a uniform magnetic field of flux density B, pointing upwards, right? Pointing upwards. An enlarged picture of the square loop seen from the above is shown in figure 4. Okay, this one, right? An aerial view is given, that is clear. Aerial view is clear, right? When the magnetic region is completely underneath the loop, the magnetic field produced by the magnetic region is directed out of the plane of the loop. Okay, first one. Sketch the variation of induced EMF psi with time t as follows. Psi with time t as follows. T1 as T1 as the time when the field just enters the loop. Field just enters the loop. Okay. Then we know E is right. We need to plot induced EMF, right? E is minus delta band over t, no? Or this is also written as minus d phi by dt. Delta band over t or d phi by dt. Right? Now when it enters, what changes is only delta a over t. Then this is proportional to delta a over t. This is proportional to delta a over t. Right? Then if we plot a time variation, right? Induced EMF is given as psi now. It is given as psi now, right? And let's say time starts from here, t1, t2, t3. Then as a time when enters the loop, okay, say then t1 is here, right? t2 when the loop is fully inside, then t2 and t3, right? So we know when it enters, delta A changes. When it enters, delta A changes. When delta A changes, there is an induced EMF, right? Since delta A, change of delta A is constant, right? We have drawn these variations in the class, right? Then let's split these intervals for the clarity. Then from T1 to T2, there is an induced EMF like this. Then T2, as the time when loop is fully inside. Fully inside means there's no change. If there is fully inside, no change of area. No change of area means this is 0. It becomes 0. Right? And when it leaves, we know according to Lenz's law, right? Always, according to Lenz's law, when enters and exits, always directions of EMFs are opposite. Don't check again and again because that's how it works from Lenz's law, right? Then from T3, again, it should be same magnitude but opposite direction. And the final variation we are getting is this. The final variation we are getting is this, right? Final variation is this, right? And in terms of these heights, they should be equal, right? If this is E, this is minus C. Same magnitude, opposite directions, right? The reason is Lenz's law, right? What causes the opposite direction is Lenz's law, right? Part 2. Write down an expression for the magnetic flux phi through the square loop in terms of B and D when the loop is completely within the magnetic region. Okay, then we know phi. Phi is written as band, no? Equation of phi is band. Then B is given as B. And area of this loop is side length is D, no? If side length is D, area is D squared. Number of turns, only 1. Then phi equals BD squared. Right? It is done. Part 3. Write down an expression for the time delta t taken for the magnetic region to pass the loop in terms of d, r, and omega. Assume that the magnetic region is at a mean distance r from the center of the disk. Okay. Right. Time it takes to pass. Then in terms of d. Okay. Then we know s equals ut. Then to pass a distance d, right? If the time takes is delta t, right? This is what happens. Now, if there is at a distance r from this loop, right? Now from this loop, there is at a distance r. So we know speed of a particle here or speed of the disk here is given by r omega. No? Speed is given by r omega at that point. If there is at a distance r, then d equals u is r omega, right? Because we know v equals r omega. Then r omega delta t, right? We need to write the expression for delta t. Then delta t is given by d over r omega. Right? It is linked to circular motion also. Right? Circular motion link right? Nice flow. Right? Starting from Ohm's law, then normal electricity, right? Ohm's law, electricity, equivalent resistance, right? Power calculations, power dissipation, and then electromagnetic induction, and now circular motion, a touch of circular motion, and so on. Right, part 4 then. 4. Using your answers to part C2 and C3 above, or otherwise, write down an expression for the magnitude of the induced EMF psi of the loop in terms of BDR omega. Right? We know. Uh, E is written as, right, d phi over dt, no? D phi over dt, right? Then E is given as psi here, that is written as d phi over dt. Then d phi over dt is, right, difference of phi over difference of t, difference of phi over difference of t. Then this is delta phi over delta t. Then delta phi is, for phi we proved something, bd squared. Then that is bd squared over delta t is d over r omega. Then d over r omega goes here reciprocal. 1d cancels. Then this equals b d r omega, b d r omega, b d r omega, b d r omega, right? Still we are in that nice flow. Still we are in that same nice flow, b d r omega, right? Then 5, taking towards a calculation, taking towards a calculation now. 5. The area of the circular disc with the radius of 62.5 millimeters is half filled with 1 times 10 to the power minus 10 to the power 13 isolated uniformly distributed square magnetic regions. Okay, square magnetic regions, right? Now this one was a square magnetic region, right? This one was the square loop, square magnetic region, right? Such 10 to the power 13 are there. Such 10 to the power 13 are there. There are no magnetic regions in the cylindrical rod of radius 12.5. Okay, see, this part is a cylindrical rod, no? This part is a cylindrical rod. No magnetic field here. No magnetic field here. Then magnetic field is only in the remaining disk, right? Magnetic field is only in this darkened volume. Magnetic field is only in this darkened volume, right? Magnetic field is only in this darkened volume only, right? That is only in this darkened volume, right? Then radius or radii are given to us to find, and there's no magnetic field here in the cylindrical part, cylindrical rod. Okay, then calculate the side length d of a single magnetic region. Side length d of a single magnetic region, take phi equals 3 and root 562.5 is 24. Okay, a root is given, then in the calculation definitely we must get this value, right? In the calculation we must get this value. Okay, then right, then if we write total magnetic field or the total area of magnetic field, total area of the magnetic field, right? Total area of magnetic field, right? Phi, from the larger circle we have to subtract the small circle. No, small circle means rod, right? Rod subtract then it is 62.5 in millimeters. In millimeters minus 12.5 squared, this in millimeters, right? In millimeters, then 10 to the power minus 6, right? 10 to the power minus 6, 10 to the power minus 6. Then at the same time we can write the total area of the magnetic field using this, no? Now one side here is, right, one, what we call the square loop here is of side length d, right? And such 10 to the power 13 parts are there, right? Such 10 to the power 13 parts are there, and another important data was given, that is half filled. That is half filled. Then this area is not this, right? Then this area is not this. This is over 2. That is half filled. That is important. That is half filled. That is half filled. Then only a half of this area. Only a half from this area. Then using this we can write, using these ones, the squares, we can write the area again as there are such 10 to the power 13 parts isolated, what they call them, square of magnetic regions inside, no? Then total area of that is, right, area of one such is d squared, and there are such 10 to the power 13, and there are such 10 to the power 13. Then this equals this, no? This is 3, right? This is 3. Then we have to simplify this now. 62.5 squared, right? Now that's a simplification. 62.5 and 12.5. 12.5 is common, right? 12.5 is common. Then when we simplify manually, right, if you see that 12.5 is common, or else we can write a square of 2. Yeah, that's better. This is the square of 2, square of a difference, no? Then we can write this as 62.5 plus 12.5 times, this is 62.5 minus 62.5 minus 12.5 minus 12.5, right? Then 10 to the power minus 6 over 2, right? Then this is d squared, this is simplification now, d squared 10 to the power 13, right, equals 3 times, right? 62.5 plus 12.5 means 62.5, 72.5, 75, right? That is 75, right? Times, this is 50, 10 to the power minus 6 over 2, right? Then keep simplifying until we get the answer, and that given hint should also be coming somewhere, right? Given hint should also be coming somewhere. Then this is 2 times 25, right? Now 75 times 75 is coming, no? Right? Now finally what I have here is d squared 10 to the power 13, and this side 75 times 75, 10 to the power minus 6. Then check the value of 75 times 75, right? So I guess it should be that given value, 75 times 75. Yeah, that is exactly that, 5625, right? Then 5675, right? Which means d squared 10 to the power 13 equals 5625 10 to the power minus 6, right? We need d, no? Then d squared equals 5625 times 10 to the power minus 19. 10 to the power minus 19. Now the given value is 562.5. Then rearrange this as now it's a simplification. 562.5 can be written as 10 to the power minus 18, no? Right? 10 to the power minus 18. Then this square root is given. Now d is square root of this 562.5, and square root of 10 to the power minus 18 is 10 to the power minus 9. This value is given. Then this is 24 times 10 to the power minus 9, right? See how nicely it's coming. Then 24 10 to the power minus 9, right? 10 to the minus 9. Minus 9 means millimicro nano, right? Then we can keep it as 24 nanometers. 24 nanometers, right? 24 nanometers, right? Nice calculation. 6. If B equals 10 to the minus 3 Tesla, and the angular speed of the spinning disk is 540 radians per second, calculate the induced EMF psi on the loop when the magnetic region situated at the circumference R equals 62.5 millimeters of the disk passes under the loop. Right, for psi we have proved an equation before. Then psi can be written as, what was the equation we proved? Psi is BD R omega. Psi is BD R omega. Psi is BD R omega. Then B is given 10 to the power minus 3, right? And D we found 24 nanometers, no? 10 to the power minus 9. Radius 62.5, but in millimeters, then 62.5 milli 10 to the power minus 3. Omega 540. Omega 540, right? Again a simplification. Again, simplification, right? Then the numbers are 24 times, 62.5 times, 54, and remaining 10 to the powers are -3, -9, -12, -12, -3, -15. Then with this 10, 10 to the power -14, right? Then this should be simplified, right? 24 times 54 times 62.5, 62.5. That is 81,000. Then this is 81,000 10 to the power -14, right? Keep it in the simplest form. Keep it in the simplest form, right? Keep it in the simplest form. Then it can be written as 8.1, 8.1 times, right? 8.1 times 10 to the power -10, no? Right? 8.1 times 10 to the power -10, 10 to the power -10 volts, right? So if needed, we can keep it in nano. Then this is 0.81 times 10 to the power -9 volts, no? 10 to the power -9 is nano, then 0.81 nano volts, 0.81 nanovolts, right? That's it. Right? That's also a nice question with a good flow, with a nice flow, right? So what I discussed today was most recent last three questions, last 3 years questions, right?